All right, welcome to the first video of 9.4. There are some special rules for logs. We have talked a lot about what a log is, right? It is the reverse of an exponent. So we've got log 2 of 32 is equal to 5, my go-to example, because 2 to the 5th is equal to 32. But if you recall, way back when, we also have rules for exponents. 2 to the 2nd times 2 to the 5th could get you 2 to the 7th because you would add the exponents. So if we have rules for exponents, you know we have rules for logs. It's basically because we're going to take these and we're going to flip these rules upside down as well. All right, but let's look at them more in context. You recall our rules. If you have 2, you can add them. Anything to the 0 power is 1. Anything flipped over, you get a fraction. Those 3 we have dealt with a lot in this section because of graphing. Also remember, if you have 2 being divided, they cancel or they subtract. 2 to the same power, you multiply. And if you have 1 being multiplied, you can distribute. So we're going to look at these rules upside down now. And we're going to look at them one by one. We've got a product rule, a quotient rule, a power rule, a zero rule, and a negative rule. Let's look at them in context, though. Staring at these in the graph, not going to be very helpful. So go on ahead and head on over to the next page. Let's look at example 1. We've got log base 3 of 12 plus log base 3 of 6. Okay. Now, if we were to convert both of the, well, I don't want to do it that way. Let's say so recall we have a rule, the one I just showed you, 3 to the 2nd times 3 to the 3rd. We're going to add them to get 5. So we have 2 bases being multiplied, we add the exponents. Since logs are, in a sense, the upside down exponents, you can't see it, but I'm making quote signs, we are going to upside down that rule. Instead of having multiplication, so we add, we have add, so we multiply. All right. Now let's look at that. We had 2 different logs. We became 1 log. Just like you have 2 different bases becomes 1 base. Very important. We smushed these things together with 1 log base 3. Now, what we call the arguments, which are not the exponents, but the arguments, those are the things that are going to end up being multiplied. Just like in exponents, the exponents are the things that end up being added. And so this would become log 3 of 72. Okay, let's look at that again. Over here, we've got log 6 of x plus log 6 of 4. I've got addition, so I can smush these into 1 log base 6. The arguments will now become multiplied. I can't really simplify this any further because I don't know x, but I've simplified this down to log 6 4 times x instead of 2 different logs being added. One more time, even if I don't know the bases, even if it's still the bases, I know that x is going to be x in both cases. If I choose x, it's going to become the same no matter what. So I can do it here as well. 1 log base x, the 2 arguments, and if it's going to help you see, put them in parentheses, right? The 2 parentheses are going to smush together to 12 times 15. Or log x, yeah, 180. Cool. That's our first rule. Our next rule, well, actually, addendum to this first rule, what do you do when you have 2 that don't match? You can't do anything. You cannot apply this product rule to this scenario. There are other rules we could do here, but this is not something I want to show you right now. Okay, so this is no product rule here. All right. Next up, we have undoing this rule. So I've got log 216 here. Why would I ever want to undo this rule? Why would I want to make it bigger? Maybe to help me solve. Okay, so if I undo this rule, I could look at this as log 2 of 4 times 4. Yeah. And then I could undo this as log 2 of 4 plus log 2 of 4. But what is log 2 of 4? That would be 2 plus 2 is 4, and I get 4. So you can expand this out to help you simplify pieces as well. Sometimes both of them don't end up being simplified, and that's okay too. For example, we have log 4 of 12. Well, log 4 of 12, if I undid this, old school, right? Oops. we have, I don't know, call it x. 4 to the x is equal to 12. Well, I don't know about you, but right off the top of my head, I don't know something when I multiply it, I get 4, or I get 12, right? 4 times itself a certain number of times, either it's 4 or 16. So that doesn't work. I'm not going to get a straight x. It'll be like 1 point something. But I could split this up into log 4 times 3, right? I could. 12 is 4 times 3, little factor tree there for you. So log 4 of 4 plus log 4 of 3. Well, log 4 of 4, what power of 4 gives you 4? That's just a 1. Again, the second part is going to be a decimal, but at least I can take out a 1. So maybe that helps. And again, why would you want to do that? It depends on what you're trying to do, right? Right now, we're just learning the tool. Later, we'll actually take this tool out of our toolbox. All right, that was product rule. Here we go with quotient rule. Same, but opposite. We also have a rule with exponents that if you have 3 to the 5th divided by 3 to the 2nd, you subtract them to get 3 to the 3rd, or you cancel them to get 3 to the 3rd. The same thing happens here. If you have 2 logs of the same base being subtracted, then you can squish them together into 1 and divide the arguments. Remember, the arguments are the things that are going to change here, just like the exponents are the things that are going to change here. You don't subtract 3 minus 3 to get 0 to the 3rd, right? You leave the log alone in the same case, same idea. And that would be our simplification. Look at it again over here. You've got log 5 in both cases. They're being subtracted, so we can squish them to 1 log, and their arguments will be divided, 6 over x. There we go. Cool. You could also reverse this process, right? We don't know really what power is going to take 3 to the and make it 27 over 5, but we could write this as log 3 of 27 minus another one, log 3 of 5. So this time I split it up into 2 logs. This first one, what power takes 3 and gets 27, that would just be a whole 3. This other one, whoops, not equal. This other one would be some kind of decimal, and so we will leave it as a log. So maybe that's something we want to do to help us graph a little bit, because that one we could graph pretty easily. Unfortunately, like the product rule, it does not apply if you have different bases. Both of these are decimals, so it's probably as simplified as can. No quotient rule here. Perfect. All right, that was the first one, very similar, or second one, pardon me. That was very similar to the product rule. Let's look at some more things you can just do with a singleton log. We have another rule that if you have 2 to the 3rd to the 6th, then you would multiply those exponents. This is kind of the undoing of that rule. If I have a log, but within that I have another exponent, well, that's exponents on top of exponents on top of exponents. And so what I can do is drag that exponent out to the outside. I know that one's a little strange. The math behind that takes a good long while to look at, but that's basically the move. You basically drag the exponent out to the outside. Same thing with variables. If I have an x to the 5th within a log, that's, think double negative. Negative times negative is positive, so we take that out and to the outside as a positive 5. Oops, let's write log b of, and now it's just x to the 1st. All right, cool. Sometimes it's not as obvious to do this rule. We know that 25 is a square, so we could rewrite this interior argument as 5 squared, right? Why would I want to do that? Because then I could take the 2 out. How did I see that? Because I wanted the 2 to come out. I saw 25, and so I decided to write it as 5 squared so that I could take that 2 out and make a smaller log. Same thing here. I'm seeing 1/8. There's several ways I could go with this one. I could call this log 3 of 1/2 to the 3rd, in which case I could take it out as 3 log 3 of 1/2. Not too bad to graph. I could also see it as log 3 of 8 to the negative 1st, which would be -1 log 3 of 8. So drag that -1 out. Or I could do a combination thereof and say that this is log 3 of 2 to the negative 3rd and have -3 log 3 of 2. And again, it depends on what you're trying to do. Graphing log 3 is not that bad, but none of these numbers that we got to take out are perfect squares of 3, right? So, or perfect powers of 3. So it really doesn't matter at this point which one we take out, but I always recommend go as far as you can. As far as you can. Take as much out as you possibly can. I can't take anything else out of the 2. All right. Last couple rules, we only really need one example for each. They're very similar. So we've got 2 to the first power is equal to 2, right? Anything to the first power is equal to itself. And so if you have a log of itself, well, what does that have to be? If I say this is equal to x, yeah, it's got to be 1. The only thing that doesn't change that power is 1. So this whole thing is just equal to 1. Same but opposite argument here. If I call this y, then I have 178 to the y is equal to 1. What's the only power that drops things down to 1? Y has to equal 0. And so we can automatically just call those 0. So it doesn't matter what base we had here. If you see a 1 in that argument, you have a 0. If you see the match, that has to be equal to 1. All right. Those are pretty much all the log rules. Okay, in the next video, I'm going to show you a couple different things. Actually, you know what? We'll put it in this video. Let's look at them together now, and then in the next video, we'll use them to solve some equations. So, looking here, I've got a couple rules I see. Again, luckily, there's not a strict PEMDAS to these things, but it looks like they're trying to imply one, what with these parentheses here. If I combine those two, I've got log A being subtracted, so 1 log A, P over Q plus 2 log AR. Now I do see a plus, I do see a similar log, but I get that 2 in the way. So I'm going to go ahead and do the reverse of that exponent rule. I'm going to move that up there. And so we get log A P over Q plus log AR squared. Now it's just log A, so I can shove them together. Log A of P over Q. Don't let this confuse you. You can just sneak that R squared up into the top there, or you can place it next to it. Same thing with PEMDAS. And now it's a singleton log. All right, let's go over here. Let's see how much we can condense this guy. I do see log A in both cases, which is great, but I do see a lot of stuff floating around the outside, so let's apply that exponent rule. We get log A of 5 to the third plus log A of 9 to the 1/2. Don't let 1/2 scare you. Remember, anything to a half power is the same thing as a square root, but we'll deal with that later. I have a plus sign now, which means 1 log, and my arguments will be multiplied. All right, so now I've got log A, 5 to the third is 125. This is the same thing as square root of 9, which we know as 3. So log A of 375. Boom. Nice, pretty, this one. All right, cool. Again, if you have any questions on it, the best thing to do is not watch the video again, but go ask your teacher. Go ask whoever is your teacher why you have a question, what the question is, have them help you out. This one's a lot longer, but I do see a lot of coefficients that I could throw in. Luckily, got to double check. It's all log base b, so I can do that. Whoops. No, there we go. Whatever. Log b x to the 1/3. Log b y to the 2/3. Whoops. So 2/3. There we go. Minus log b s to the 1/4 minus log b t to the 2/3. Okay. Let's see. I'm going to add those two guys, and by that I mean I'm going to shove them together into a log b x to the 1/3 y to the 2/3 minus these guys to the 1/4 log b t to the 2/3. Since these are both minuses, I'm going to drop them both to the denominator. Log b x to the 1/3 y to the 2/3 over s to the 1/4 t to the 2/3. Don't overestimate this subtraction's power. If you drop 1 to a denominator and then you have another one that's minus, you don't get a second denominator. It just also goes underneath. Okay, it's just as if you're dividing by 2 things instead of 1. We could change these to some radicals and simplify. That would depend on what we were trying to do, but we did condense this down to a singleton block. The last thing we're going to do is expand this guy because he's already condensed. He may need to expand. So what could I do here? How far could I take this? How big could it become? Well, first thing I can do is probably that. Notice how this one usually takes the first move. Usually deal with those exponents, bring it outside. Now I see a subtraction because of division. Yes, both of these are going to get a 3. Log 6s squared. And then maybe one more thing I can do, take that out. B minus 6, notice I multiply the 2 and the 3 because I have 2 going out and 3 going out, which means 6 goes out. And that's probably about as expanded as it can go. All right, not an easy thing, these rules. You got to get used to them. There's a lot of new subtlety to it, so take some practice, ask your teacher any questions, and we are going to use them in the next video to solve some equations, and I will see you there.